the software first. I'm sure there's some of you out there listening in this meeting who are maybe familiar with our tool, maybe have used it a little bit. Some of you may be brand new to it. So I'll go through the FaultTree tool a little bit first, and then we'll talk about these Lopa, how you might use FaultTree in part of a Lopa approach to analyzing layers of protection. So just starting with fault tree analysis, let me just give a quick overview again. If there's anybody in the conference or in the meeting who is not familiar with our software or with fault tree analysis generally, just a quick definition: fault tree analysis is a deductive approach to hazard analysis. It starts with a hazard or some excuse me, my computer's switching over. I forgot it always wants to do this. There we go. Okay, so fault tree is a deductive hazard approach. It starts with some sort of hazard that we want to avoid, be a hazard or typically a failure, something catastrophic or something that we want to avoid and try to prevent. It tries to determine, it's a methodology to try and determine the causes of this hazard, of this top event. So we're looking at usually component failures or events, operator events, things like that, that could cause some sort of hazard to occur. It's a graphical representation. It shows graphically how these failures interact with each other, not necessarily the physical interaction, but the logical interaction. It shows this by showing this hazard as a top event, and it's connected via logic gates to the component failures, which are called basic events in the fault tree parlance. Fault tree analysis is qualitative in the sense that you can just use it to look at the system qualitatively, look for things like single point failures or different failure paths, or look for common cause failures if there's one event that could cause multiple different failure paths. You can do a qualitative analysis, but most commonly it's used for a quantitative analysis. And that's where you would put in some sort of failure data or probabilistic failure information into the basic events to tell the program, to tell your fault tree program, or if you're doing it by hand, which I'm not sure why you would do that when you have a nice tool like the Reliability Workbench out there. But you can put failure data information into the tool, and it will use this to be able to produce a quantitative analysis. Here, in that type of analysis, it would produce what we call an unavailability, or maybe a probability of failure, or of failure on demand, depending on your industry. It also can calculate things like a failure frequency, how often failures are expected, and a mean time to failure, and a number of other measures. And we can take a look at that when we jump into the program. Let me do that right now. I'll jump into Reliability Workbench, and I have a fault tree open. I hope you can see my screen still. I'll give it a second to refresh on everybody's screens. Now I have a fault tree. My top event here, my hazard that I'm trying to mitigate or as I'm trying to avoid, is a total loss of cooling event. This fault tree models a cooling system, and what I don't want to happen is I don't want the cooling system to fail with a total loss of cooling. So I want to know what are the potential causes of that. So I have my top event. This logic symbol here, you're probably familiar with it, even if you've never seen a fault tree. They're commonly used even in other usages in other industries. This event, logic symbol represents an OR gate, and it just means that the occurrence of either of these two inputs will cause the occurrence of the top event. So in this simple fault tree, I have a total loss of cooling, which occurs if my heat exchanger, which is a critical component in the cooling system, fails, or there's no coolant to the heat exchanger. Now I can drill down through the entire fault tree explaining it, but I don't think we need to go through that within the software. Just wanted to sort of give you a quick overview of the fault tree and how to read it. Now, again, many of you may have used our fault tree software in the past, so I don't want to bore you on the details of, or even if you haven't used the software, you're probably familiar with the methodology, so I don't want to bore you on the details of how to read a fault tree. I'll just go through some of the few basic features of the software so you can understand what its capabilities are. Firstly, it makes it very easy to build these graphical fault trees. There's toolbar buttons to create the fault trees and add gates and events. I'll just go through very quickly, just adding a few just to show how that works. I have a button to add a new top gate, and I have a button to add gates, so I can just click where I want to add new gates into my fault tree. And then I have buttons to add basic events. So I can very quickly build up a fault tree. Now this is building up the graphical side of things. Okay, by the way, when I'm done with adding things, I want to clear my add mode so I can now go and edit things. Once I've added them, I can go and do things like change the gate logic and add names and descriptions. That's either done via double-clicking on an item to bring up its properties dialog. There's an option where you can change the logic symbol for the gate type, and also facilities to change the ID and description. So it's fairly simple to use, and that gives you the qualitative side, the graphical side, where I can draw those logical interaction of failures. The second part would be to enter failure data into the fault tree. And again, that also is fairly simple. Failure information is entered, probabilistic failure information is entered for the basic events. I can just simply double-click on any one of my basic events to open the edit dialog. And then there are buttons for adding failure data. I'm going to use this button right here to create a new local failure model. That means this failure data will be specific to this basic event. There are a number of different failure model types, each one specific to the types of failures you might have in the system. So for instance, fixed failure model type allows you to enter a fixed probability of failure or unavailability. Rate model type would allow you to enter a failure rate or a repair rate. It depends on what sort of information you have, what sort of failure information you have about the component, whether or not you know the probability of failure or the rate of failure, or maybe the rate of failure with a test interval. If you're using a dormant failure, you might specify a test interval. One of the inputs into a fault tree is the failure data if you're doing a quantitative analysis. So you have to get it from somewhere, usually a standard or a maybe manufacturer or historical data has to come from somewhere. The program does have features to help you figure out a failure rate if you don't know one, but that's probably a topic for another webinar. I don't think we have time to get into that in this overview. It's not really going to be our focus. I just wanted to quickly show and point out how you can enter failure data. So I'll just enter some information off the top of my head. By the way, the units the program doesn't care what your units are so long as that they're consistently entered throughout. So these could be per year, per million of hours, whatever I want them to be. So I'll enter just to make up some information, click OK, and now that failure data that I've entered in this basic event can now be used in the quantitative analysis of the tree. Okay, now I'm going to go ahead and just delete all this information I entered because I'm going to want to run this tree, and I don't want this extra information, this extra partial information sort of gumming up the works. So we'll just go through and I'll run an analysis on this example tree that I had earlier so we can see what sort of outputs the FaultTree Plus module gives us. And keep in mind, that's really the two basic stages of the fault tree. First, you build it, creating the logical hierarchy or the logical interaction of failures. And then you add the probabilistic information. And that's really the only two pieces of information the program needs to know, the logic of the system and the probability of failures for each basic event. So I'll click my green traffic light button up at the top to perform the analysis, run the analysis, and we'll just take a look at a few of the results. So if I click on the Q equals button, I can get the results. Some of them are shown underneath the gate, so I see a Q equals. Q equals in the fault tree parlance means unavailability or the probability of failure. So I see unavailability. That means basically the way you might read that is there's a 0.1443% chance that at the end of the lifetime, when the system is our designated lifetime, that the system will be failed or unavailable. The frequency tells me about how often that is going to occur, 0.3717 failures per unit time, which I believe in this example are years, about 0.3717 failures per year, or a little more than one failure per 3 years. Okay, so that's just a quick look at some of the information you get. And again, maybe in more time or in our training session, we can get into some of the other useful features that the program will give you, such as importance analysis, which helps you identify the weak points of the system, or cut set analysis, which is that qualitative analysis I was talking about earlier, where you can look for things like single point failures and common failure paths. Okay. So again, that's a very quick and brief overview of the fault tree. I don't want to get too bogged down into it. We're going to talk about a few other topics today that I want to make sure that we cover. But before we move on, Jeremy, have any questions coming? Is there anything that you'd like me to address?
Let me look at 1 second. Someone's referring to an older version of FaultTree, obviously one of our users. In FaultTree 10, you could add events and gates in the dialog edit menu of the gate once you double-clicked on the gate. Have we added that back in? I think it was gone for version.
Right, yeah, so there was in version 10, there was an ability to add gates and events from within the gate properties dialog. That feature was removed in Reliability Workbench version 11. I think the developer has more information on why it was removed. I think certain users thought it was confusing, and it just sort of tended to clutter up the interface. I know a few people that liked it that way. I personally never used it that way. I found it more easier to graphically interact them. But we haven't, that's not in the current version. Then again, we do respond to user requests. So if there are a lot of users who preferred that, we might look at adding that back in.
Yeah, so I'll put that in our request for user upgrades, and we'll take a look at how many of those have come in.
Okay. Was there anything else that you'd like me to address?
No, that's good for now.
Sure. Okay. Again, remember, if you have any questions, you can type them into the chat. Jeremy will be reading through them. Probably many of them he'll be able to answer himself, just to type back to you. But any that he thinks are of general interest to the rest of the audience, or that, well, he's a sales guy, so he doesn't know every little technical aspect of the software. Anything that he can't answer, he'll refer to me. Okay. So let's jump back and talk about the next topic, which is event tree analysis. And this is, I'm just bringing this up because it is relevant to our topic of layer protection analysis, which we'll get into later on. Event tree analysis is a good component to that. Now, I'm willing to bet that of our users in the web meeting, those who've used the software, even those who have a lot of experience with the FaultTree tool, probably many of them have not used the event tree analysis tool. Now, event tree analysis, this comes with the FaultTree package. If you purchase FaultTree, it comes with the event tree module as well. And it's a separate but related type of analysis to the FaultTree, very often used in conjunction with FaultTree, but can be useful for solving other different types of tasks. Okay, just to give you a quick definition, event tree analysis is an inductive approach, whereas FaultTree was deductive. Remember, we started with our hazard and worked backwards to figure out what would cause it. With event tree analysis, we start with the hazard and then work our way forwards to see what could possibly come next. What are the potential consequences that could follow based on the status of various mitigating circumstances. Event tree analysis works by evaluating these event sequences. We have a sequence of potential mitigating circumstances, and based on the status, that will lead us to a particular consequence. These consequences could be range from things like safety consequences. Potentially a failure might cause a loss of life. Maybe there's a financial risk to it or an environmental impact in terms of a toxic spill. So we can assign consequences and also assign weights to the consequences. So some event sequences might lead to more severe consequences than other event sequences. So weighting the consequences allows us to compare different event sequences, the potential risks of different failure sequences. And by risk is just a fairly simple concept. Risk is just the how bad it is. It's usually calculated as the weighting times the frequency. How often does it occur, and how bad is the occurrence, is the consequence. So event tree analysis can quantify risk. And again, it uses the same quantitative methodology as FaultTree. Again, I'm not getting into it in this webinar. It's part of more under the purview of our training session. But the quantitative methodology, the Boolean algebra logic, and the quantitative probabilistic methodology that fault trees use can also be used in event trees to solve it. If you're familiar with that, you know what I'm talking about. If not, don't worry about it for now. Although maybe a later webinar we can discuss the actual math behind a fault tree. Sometimes you see fault trees and event trees together referred to as bow tie events. That's because if you turn the fault tree on its side and attach it to the event tree, it kind of looks like a bow tie. Where we have our top event is sort of the middle. To the left is the fault tree, where we look at our threats or the possible failures which could cause that top event. And these are basically our control measures. Mitigating these threats or these failures can mitigate the occurrence of the top event, can try and prevent it from occurring. To the right of our top event, on the right side of the bow tie, we have our basically our recovery measures. This is where our various consequences can occur, and based on the status of our mitigating or protective measures, we can mitigate those consequences. So this is sometimes why it's referred to as a bow tie, because if you draw it, it kind of matches the profile of a bow tie. Okay, so let me jump back into the reliability workbench, and now we'll just take a look at how event tree might look, and how to read it, and how you would use it. Okay, I'm going to click down here, and I get my event tree. Now, again, event tree is read in a left to right fashion. The leftmost column is referred to as the initiating event. In this particular event tree, the temperature surge is the initiating event. That might be the top event of a fault tree. Often a fault tree is used to quantify the sequence of events in an event tree. In this particular example, this temperature surge event is actually just a basic event. It's just we've just directly specified a probability, or rather a frequency of occurrence. So my frequency here is 4 occurrences per unit time. And again, in this example, my units are in years. So 4 occurrences per year of this temperature surge hazard. What we want to know here, what we're evaluating with this event tree, is the effectiveness of our protection systems in preventing hazardous consequences from occurring, given that the temperature surge hazard has occurred. So basically, this is a very simple example. I'm just keeping it that way while we're for learning purposes. But here we have 2 protection systems: a primary cooling system, which is quantified by that fault tree we were just looking at earlier, and a secondary cooling system, which is one where we've just estimated a probability for it. Now, to calculate the consequences, at the very end I have various different safety consequences depending on the availability of the cooling systems. The temperature surge might cause fatalities, probably through the breakout of a fire or an explosion or some heat generation issue. Now, based on the status of the cooling systems, that can lead us to one of these different consequences. The consequences are quantified very simply by applying AND logic at each branch in the event tree. It's a little unclear here, so let me just turn on an option to show what each branch represents. Show branch type, I think that's the option I want. Okay, success or failure, there we go, that makes it a little clearer. Success means the success of that system, failure is the failure of that system. So if the primary cooling system is successful, then we're not going to have any bad issues. If the primary cooling system fails, then depending on the status of our secondary cooling system, that would lead to either 1 fatality or greater than 8 fatalities. So to quantify these terminating branches, we just apply AND logic at each point here in the tree. So in order to lead to the greater than 8 fatalities consequence, we have the frequency of the temperature surge, multiply that by the probability of failure of the cooling system, multiplied by the probability of failure of the secondary cooling system. That will lead us to this greater than 8 fatalities, the frequency for that. So we'd read that as 0.001265 occurrences per year. Or what's that come out to? A little bit more than 1 occurrence per 1,000 years. Okay. Let's see. Let's take a look at.
Oh, go ahead.
Oh, go ahead, Jeremy.
I was going to say, let's. There's a couple questions.
Okay.
No, first of all, for those that have raised their hands, make sure you post your questions in the questions dialogue section of the website. of the go to webinar menu. That'll be the easiest way to address your questions. There is a question that came in. Backing up a little bit. When you have a failure mode of true or false, how does that factor into the calculation? Is it the equivalent of a failure rate of 50%? I think we're going back to the
FaultTree, yeah.
Yeah.
Okay, so you're talking about a failure of true or false. I assume that the users or the attendees probably referring to house events, which is a concept in fault trees. There's a setting for a logic mode where you can set a true or a false house event. And what those are used for is for configurational events within a fault tree. What a true house event means is that the event is always occurring. Another way of saying that would be it's always failed, or that it has a probability of 1. A false house event is one that does not occur, has a probability of 0. So you choose which logic mode you want, true or false, and basically the tree will treat it as a probability of 1 for a true house event, or a probability of 0 for a false house event. Typically these are used for configuring or reconfiguring the tree. You can use it to turn on or off different branches within the tree. As far as how the program actually calculates it, house events actually don't appear in the cut sets. They don't really appear in the quantitative calculation side. Since the probability is always either 1 or 0, the impact that has on the tree is usually to remove or add a branch in. So the event itself, its probability doesn't show up in the calculations. Rather, it just permits whether or not some other aspect of the tree will show up in the calculations. I hope that answers the question. If that answers, please let Jeremy know in the chat, or if not, please clarify in case I misinterpreted.
No, that sounds good, Joe.
Okay. Did you say there was another question as well?
No, nothing for the group.
Okay. Okay, so let's just take a look back at this event tree. Again, event trees are actually also very easy to build up as well. I'll just very briefly show it and then delete my work so I don't mess it up before we take a look at the results. To create an event tree, you just click the Add New Event Tree button, and it's actually even simpler than the fault tree. You just tell it how many columns you want to begin with. We'll just start with a default 4 initial columns. So I get the event tree automatically laid out. I don't have to draw it or anything. However, I can manipulate it. I can add and remove columns. There's a button to add a new column, where I can just select the column and press delete to remove it. You can also add more branches. There's buttons to add null, success, or failure branches. You might have more than 3 branches. That's a more advanced type of event tree where you talk about partial failure. This is a little more advanced than I want to get into in a quick overview. But you can do some rather advanced non-binary event tree modeling options, where the choices are not simple binary choices. To apply quantitative data is always applied via gates or events, typically associated with the columns, but again, in one of the advanced topics is they can be associated with individual branches. So to associate something with a column, I just double-click on the column, and I can pick a gate or an event to associate with this one. So I might pick my, I think I have a fire event. And that means that this initiating column's frequency is quantified by that fault, or by that event that was associated with it. So I can see that event in my events list on the left-hand side. I think it was this one right here, fire starts. And so whatever failure information I've entered for that basic event is what will be used. If I use a fault tree gate to quantify it, so let me just pick maybe my cooling system. That means that this column, the failure and success branches, are quantified by that gate. So the program will first run the analysis on that gate to calculate an unavailability, and then it uses that unavailability and availability, the one minus the probability of failures, the probability of success, to determine the probabilities at each failure and success branch. And then again, actually calculating consequences, which are again assigned via the consequences. I can add them from down here. I've already added a few consequences. I can just drag and drop them onto my event tree. So event trees are actually, it might look a little daunting at first if you're unfamiliar with it, because it's a new type of analysis, but it's actually very easy and very simple to build up. Okay, so I'm just going to go ahead and delete all this because I don't want it again to mess up what the system
Joe,
already
before
has.
you get out
Sure.
of the event tree, there's a question maybe you could answer while you're in there. Someone's asking how you can select more than two options, for example, success and failure. So maybe we should go into a little bit of how the branches attach to a fault tree to make more of a complex calculation than what you're just seeing here visually.
Sure, right. Okay, so I mentioned earlier that you can have more than a simple binary fault tree. Let me just start by adding a new one just to show how this works. Let's just start with 2 columns. Okay, so a basic event tree will be binary. Every column will be success or failure. Some cases you might want to have more than that. You might want to have partial failure or maybe degrees of success. Sometimes this is used to measure different exposure levels, or for whatever reason you might have more than 2 possible outcomes. Now if we want to do that, and again this is a little bit more of a complex topic, so I'll try and keep this simple enough. I'll add a new column here. I'm going to just connect it with single null branches. The first thing you want to do is add more branches. To do that, I select the preceding column, then just click, let's add a couple more branches. So I can add arbitrarily any number of branches. So let's say I'll put 4 right here. Now, when you're doing this, when you're having this partial failure or more than success and more than just simple binary choices, rather than assigning the probability to the column, as in the past, or as I just showed, you can assign the gate or event to the column, and the success and failure branches are based on the availability or unavailability, respectively, of that gate or event. Rather than doing that, what I can do instead is assign a gate or event with a specific branch in the event tree. So I can pick a particular, I can say, partial gate failure or partial event failure. And then a particular event, so let me go back and pick a, say, my fire event, will be associated with this branch. So what that means is the probability of this branch comes from a specific basic event, so, or a gate. So that way I can assign different basic events to each one of these branches. And then when the program evaluates it, it determines the probability of each branch as the probability or the unavailability of the gate or event associated with the branch. Again, if you're just new to event tree, this might be going a little over your head. Don't worry about that too much. It's more of an advanced topic for more complex event trees. Jeremy, please, if that was your question that I answered, or if I didn't answer it successfully, please let Jeremy know in chat, and he'll let me know.
No, I think that answers the question, Joe.
Sure, okay. You guys are asking some advanced questions. You must all be expert users already. Okay. Okay, so let's just take a look at the results that we get from an event tree. I'll just use my green traffic light to rerun the analysis. We got the frequencies as we had before. And let me go back into my Q equals. Before we were looking at gate results, but we can also look at results for individual consequences. For instance, how often does our greater than 8 fatalities consequence occur? Frequency and the cumulative frequency. Again, we can also view importance analysis. What are the weak points? What are the events that are most likely to cause it to occur? And cut set, so we can do a qualitative analysis to look at the individual failure paths. But perhaps most interestingly is we can look at the risk. Here we have our 4 different safety consequences. Keep in mind this event tree only had 2, but there's another event tree in the project that has 2 more. So we're looking at each different consequence, its frequency, which the program calculated, the weight, which is assigned. In this case, it might be like the number of fatalities, how bad it is. And then the point risk is very simply the frequency times the weight. This allows us to compare the severe consequences, like the greater than 8 fatalities, with the less severe, like the only 1 or 2 to 8 fatalities. So you can see the highest point risk comes from our greater than 8 fatalities consequence. And up at the top, we have a sum of the risk of all of them. And this basically, if these values here, if our weighting refers to number of fatalities and our frequency is number of occurrences per year, this summed point risk right here basically means, on average, how many fatalities per year would we expect? So 0.06382 fatalities per year, or a little more than 1 every 20 years, which is probably an unacceptable risk level. We might want to look at that. Okay. Okay, any questions on the results before we move on?
I'm going to take a quick look here. And back to the event tree, and when you're adding multiple branches, is it true that the total would equal 1?
The interesting thing is the program doesn't necessarily enforce that. Typically, you'd set it up that way. When you're creating the basic events, or that would apply to the partial event failure branches. Typically, you construct them in such a way that their probability is 1. The program doesn't enforce that, which means you can end up in the interesting scenario where you have non-mutually exclusive branches, where you have 2 branches that can simultaneously occur. Now, in traditional event trees, that's usually avoided, but the program doesn't enforce that. Although I think I'd have to look for it. I thought there might have been an option, although it's been so long since I think it might be this one right here, check event tree branch probability consistency, which will check to make sure that the branch probabilities sum to 1. But that option's off by default. So you can turn it on if you want to make sure that the combined sum is 1. But you can turn that off if perhaps sometimes you don't want to consider every single consequence. You only want to consider the bad ones. Or maybe you have a scenario where branches are not necessarily mutually exclusive. Again, that's another really advanced question. So you guys have some good questions. Okay. So that's a good primer on FaultTree and event tree. Just gets you started and on understanding the basics and how they work and how they integrate with each other. Fault trees can be used to quantify the events, the sequences in an event tree. So from there, let's move on to that other topic we advertised, which is Lopa, or layer of protection analysis. Now, Lopa is really a separate type of semi-quantitative analysis type. Usually, if you're doing a traditional Lopa, you would not be doing it within a strongly quantitative tool like Reliability Workbench, like the FaultTree module. Typically, it's more of maybe something more of a HAZOP coupled with some very simple math, like Excel spreadsheet style math, where you just investigate all your different layers of protection, just read into them, and apply some very simple math. Maybe you'd have an engineering team to discuss what layers of protection you have, how they work, and what their probabilities of successfully working are, and then just apply some very simple math to it. One of the requirements of traditional Lopa is that the protection layers be independent, and that's partially because of the simplistic math, that semi-quantitative simplistic math that a traditional Lopa would use. It would work basically like that event tree that we were just looking at, where you just multiply probabilities of each layer of protection successfully operating. Now that mathematical law, that probability law, that's taking advantage of, assumes independence between layers of protection. And the whole point of this is to figure out how successfully or how well you're mitigating the risks that could occur following a hazard. So here we had a loss of cooling as our hazard, and we want to know how well that we were mitigating the risks and preventing a fire or an explosion or whatever the consequences that could occur. This Lopa allows us to evaluate that and gives us really an objective way of looking at how well we've mitigated our risks. Now, you can go a little bit beyond Lopa, beyond what a traditional Lopa can accomplish when you couple it with event tree and also fault tree analysis. You can extend this methodology of evaluating your layers of protection by using it with event tree. One of the first things you can do, and this might be blasphemy to a traditional Lopa user, and one of the things you can do is evaluate non-independent layers of protection. whereas Lopa confines your layers to be independent for the mathematical reasons. With FaultTree methodology, with the complex mathematics that it uses, the Boolean algebra and the cut set methodology, it can evaluate non-independent layers. Another thing it can take into account is partial mitigation. Usually with a Lopa, we're looking at the hazard, and then one of the definitions is that each layer of protection has to be capable of fully mitigating the consequences of that hazard. So we're probably only looking at one particular or set of consequences, and if a single protection layer operates successfully, we assume the consequences don't occur. When we're extending Lopa by use of FaultTree, we can consider a layer of protection that partially mitigates, that may prevent the worst parts of the hazards, but still is not as good as a full mitigation. Also, we can, due to that, taking into account partial mitigation, we can track multiple consequences. Maybe if we don't mitigate at all, we have some disastrous consequence. If a partial mitigation would result in a less severe consequence, so we can take into account there are multiple levels of consequence that might occur. The event tree, again, coupled with FaultTree and using this quantitative methodology, can calculate our current risk level, very similar to how we would do with a traditional Lopa, calculate what our risk level would be, and also helps us figure out what we can do to lower that risk. Suppose we're given a goal, a reliability target that we're supposed to meet. We can see, it can help us figure out how far off we are from the goal or if we're meeting it. And it can also, coupled with the FaultTree methods like importance analysis, it can help us figure out how to, where to focus our efforts to lower that risk. So let me jump back into the reliability workbench. And this time I'll open up another project that has a slightly different example. Okay, in this case we have our top event, our hazard, is a flow regulator fails open. To give you a little bit more information on the system, we're pumping a chemical into a reactor vessel, and there's a flow regulator which is supposed to limit the flow of the chemical, into the reactor, designed to maintain a safe pressure and temperature within the reactor vessel. If that flow regulator fails, and it's probably an entire system, there's going to be sensors and a computer that tell the flow regulator how to behave or how much fluid to allow in. If that system fails, then that can cause the hazard of an overpressurization or an overtemperature in this reactor vessel, which could potentially lead to a rupture of the reactor vessel. And that would be very bad. So that's what we want to avoid. Now, I haven't built a FaultTree to demonstrate the failure rates or the failure frequency of this flow regulator fails open. That may have been done separately. But what I'm doing here is I'm analyzing our different protection layers. There's two primary protection layers. One is an alarm response. If the flow regulator fails open and there's an overpressurization or overtemperature event in the reactor vessel, we have separate sensors from the flow regulator system, which will sound an alarm and tell our operator that there's an unsafe condition, so he can throw the switch to shut down the process. Shut down. We have presumably we have block valves or something that can shut down the inputs to the reaction. There's also, in addition to that, a automated sys loop, safety instrumented system. If you're not familiar with this, with the acronym or the initialism, a safety instrumented system, which is an automated system, which basically does that same thing that the operator would do. Is it detects the overpressurization and automatically shuts down the process. Now, if both of these protection layers fail, then we have a pressure relief valve which can vent some of the chemical in the reactor vessel to lower the pressure. Now, if both of these fail, these systems fail, but the relief valves operate successfully, we'll still have a minor release of chemicals, and there might be some environmental damage and OSHA fees or something like that associated with it, but it would not be nearly as bad as having the entire reactor vessel rupture, spilling all its contents and perhaps creating some extreme hazards. So in here, we've identified two potential outcomes, two potential consequences with a partial mitigation on the pressure relief valve. So that's one way we've extended Lopa. Another thing is these alarm response and sysloop trees are not independent from each other. Now, in a traditional Lopa, you just basically have to throw it out or just treat it as one protection layer, and probably play it very conservatively because of the math involved. But with a fault tree, fault tree and event trees together can more accurately model the dependency between these two columns. Let's take a look at those two event trees. The alarm response, there's the inputs to the system are the pressure and temperature sensor inside a reactor vessel. We have an alarm signal processor that will take the inputs from those sensors and sound the alarm if the inputs are too high. And then we have the operator who either doesn't respond because he's unavailable or he doesn't remember what he's supposed to do. Maybe he's Homer Simpson is asleep on the job, or because the alarm unit itself has failed and doesn't sound, or the blinking light on his control board and the bulb is out in the board or something like that. The sysloop is very similar. We have the same inputs, and here's the dependency between the two. We're using the same pressure and temperature sensor inputs for both the manual and automatic systems. In the automated sysloop, we also have the logic solver and then three three outputs, 2 isolation valves and a pump power removal that we can use to stop the flow into the reactor vessel. Okay. So all said and done, once we've hooked everything up, we can just run the analysis, and it will tell us calculated. This is the value we've entered for we figure about 0.02 times per year, or about once every 50 years, our flow regulator system might fail open. We have alarm response with an unavailability of 0.05, or about 5% probability of failure on demand. Our sysloop is a little bit better, probably because we've removed the human element, so we don't have to worry about an operator being available. But the sysloop has a probability of failure on demand of about 0.1%. And then we have our pressure relief valve, the probability of it being stuck closed. And in the very end, if we apply this math, and again, it's not going to be a simple multiplication through at each branch, because we have to take into account the dependencies between these two columns. But in the very end, what we end up with is a frequency for the different events. We've ranked the major release and minor release. Let me just show the weighting. For the major release has a weight of 10. I think the minor release has a weight of 1. And that could be fatalities. It might be tons of toxic material released into the environment, whatever that value represents. We've calculated first a frequency, and then we can go to our result summary to view the risk. Let me go over to my risk level. So we can see the frequency times the weight is the point risk for each consequence. And then we sum them up. And again, if it's maybe it's tons of toxic material released into the environment per year. So we say 4.318 times 10 to the negative 6 released per year. Okay. Now suppose we've set a, actually maybe before I would go on, I should pause and ask for questions. Jeremy, have there been any questions?
Nothing specific to the group.
Sure, okay.
If anyone has any questions, that no matter what it is, just put in the questions dialogue, and I'll probably just answer you privately.
Okay. Just to go on, so suppose we've set a goal for ourselves of we want a point risk no greater than 1 ton per million years, or something. 1 ton of release of chemicals per million years. That's what we've defined for our point risk. We can see we're not meeting that. We're above that. 4.318 times 10 to the negative 6 is greater than 1 times 10 to the negative 6. So if we divide them, we get we're exceeding our point risk by a factor of 4.318. What that value tells us is the further risk reduction that we would need in order to meet our target. So in order to meet that target, maybe what we need to do is add in somehow increase our risk reduction factor by about a factor of 4. Now, risk reduction factor is actually something that the fault tree can show So one of the options that you have to appear on FaultTree gates, right now I'm showing a frequency. Are we not retaining results? Let me just change a couple options. Don't worry too much about what I'm doing. I just wanted to view the results for different levels. Okay, right now it's showing an unavailability value. Risk reduction factor is basically 1 divided by the average unavailability. And that's an option that I have within the FaultTree. So I can see what my risk reduction, here it is. I just set this to risk reduction factor for my displayed gate results. Now it's showing me the risk reduction factor that this system is giving me. It's reducing my risk by a factor of 20. My sysloop is reducing my risk by a factor of close to 1,000. You who are in the process safety industry might recognize that as being close to a SIL level 3. SIL safety integrity level rank 3 is a risk reduction factor of 1,000 or greater. So that basically tells you how much risk reduction I'm getting from each system. That little bit of math that I did, dividing my point risk by my target, tells me how much further risk reduction I need. Maybe I need an extra layer of protection with a risk reduction of 4, or maybe I need to increase one of my current systems' risk reductions by a factor of 4. Let's look at one of the ways the software can help you when we apply these FaultTree methods. One of the things I mentioned earlier was importance analysis. I showed it in the results summary dialog. It can help us figure out weak points. What's the biggest contributor? So if I go to my risk and look at the importance analysis, it will show me basically which basic events are the biggest contributors to the to that risk level. What's called the Fussell-Weasley, which is a funny name for it, tells us basically what percentage of the risk is contributed to by each component. So you can see it's actually coming from my sensors, my temperature and pressure sensor, which you probably could have guessed because they power both the sysloop and the manual alarm response. So those are 2 big contributors, each one individually contributing to about 37% of the risk. And then also additionally, the common causes, which is this third event right here, the common cause between those 2 sensors is an additional 37%. So maybe if I focus my efforts there, maybe somehow I could make them more reliable, and that would have the biggest impact on lowering my risk. And then actually here, the risk reduction worth and the risk achievement worth can help me with that. The which one? The risk let me make sure I have these right. Yeah, the risk reduction worth would be how much better my risk would be, how much lower my risk could be if that component was perfectly reliable. One of the things that I might try and do is I might try and change my test intervals. Maybe if I inspect these sensors more often to look for dormant failures, maybe then I can mitigate my risk. So let me just do that quickly. I can change my test interval. Let's say right now they're being inspected once every 6 years. Maybe we could do once every 2 years. And I'll rerun it. And then let's take a look at the results again. And now our point risk is almost there. Let's try every 1 year if we test. This is sort of the type of what-if analysis you can do. Okay. My risk summary. Now I'm down below my target of 1 times 10 to the negative 6. So basically the program showed me where my weak points were. I came up with a potential method of addressing the weak points, and that was to inspect more frequent maintenance inspections. And that by doing that, I've stated that I can lower my risk and get it beneath my risk goal. Okay, Jeremy, any final questions? At this point, we might as well open it up to Q&A, any general questions that might be, that anybody has.
Yeah, Joe, I think you went over this, but could you just quickly show how the event tree is linked to the fault tree again really quick?
Right, again, because that's a little obscure. It's not graphically displayed, the link between them. It's basically, in this particular example, they're linked through the columns. So I've created a fault tree gates. I've created some fault trees. You can see them up on the left-hand side here, and I've also created some basic events as well. These are assigned to the columns in an event tree. So this alarm response, if I double-click on it, you see the type is set as gate, and the object is set to alarm. That means this column is quantified by the fault tree gate alarm, basically this one. Whatever value is calculated for this gate is what's used for the probability of this column, at least for the success and the failure branches. So the failure branch is the unavailability of this gate. The success branch will be the 1 minus the unavailability. And again, that's simplistic. That's not taking into account the further behind-the-scenes calculations. But that's how I'm telling the program what values to use for the probabilities in these branches. You assign the gates to the column. Again, you can also drag and drop. You can drag and drop basic events or gates onto the columns. I hope that makes sense.
Yeah, that looks good. Let's see. Can you quickly show how to set up test intervals in the events, Joe?
Sure, that was something I skimmed over kind of quickly. Like this, there's a couple different ways I can interpret that question, so I'll try and be as thorough as I can. Test interval is part of the failure model used for a specific, used for each basic event. So let's take a look at, say, my pressure sensor. The failure model type that it's using is actually our IEC 61508 failure model, and one of the inputs for that failure model is test interval. So that's one way of entering the information, is depending on the failure model type you've chosen, you can enter a test interval. However, I think that what the user might have been asking was about that generic test interval that I had shown how to change it. It's possible that you have within your system, for instance in this system, I have several different components that are all tested on the same interval. My pressure and my temperature sensor, I test both of them at the same time. So I might want to be able to change them at the same time. I don't want to have to go, if I want to play around with different test intervals, if I want to do a what-if analysis, I'm not going to want to go to each one individually. Instead, I'm going to want to make it so I can just change one thing and have it affect all the components that use that generic test interval. That's what I've created here, is a generic test interval. There's a button on the toolbar to create a generic parameter. You can select what type of parameter type it is. So you can make it, for instance, a test interval. And that's what I've done for this generic parameter right here. I've created a generic test interval. Now, when I'm editing a local failure model, one that's attached to a particular basic event, when I have a test interval field, you'll see this little drop down to the right-hand side. That allows me to choose from any generic parameters I have that can fit into this field right here. So what I've done, basically what I've done is I've created a generic parameter for a test interval, and I apply it to several different basic events. And then when I change that one generic test interval, every basic event that uses it will also be updated. I hope that answers the question.
Yeah. There's a few additional questions. I'll probably have to answer after the meeting. I think we're at almost an hour, which means we're statistically just going to start losing people here soon.
Yeah.
So anyone that had questions that they posted that have not been addressed, I'll be sending you emails to respond to those questions, as well as I'll send out some information on this meeting. Let me just put up my contact information really quick. I would assume that most of you already have my contact information since you received the invitation to this meeting from me. But let me just put this up really quick. So my name's, again, Jeremy Henick. Joe Bellin's been on the line. If you have any questions about the software, please let us know. This is one of many web meetings that we've done. We do them kind of on a infrequent basis, a frequent, infrequent basis, depending on when both Joe and I are in town. So please watch for future web meeting invites, and we appreciate you attending the meeting today. And you will be receiving a follow-up email from me in case you had questions you posted that weren't answered or you want information like the slides. Okay, thanks, Joe.
Thank you all for attending.
Thank you. Bye.